Welcome to Section 3. In this section, we're going to talk about different ways in which you can improve individual models. Specifically, in this section, we're going to talk about how to modify model options so that you can improve a model. We're also going to talk about how to choose different models so that a second or third model might actually do a better job than the original model. We're then going to talk about how to remove noise, how sometimes additional predictors end up getting in the way and make it more confusing for a model to find the best results. After that, we're going to talk about how to do additional data preparation, where you may want to create additional fields so that you can further improve your models. And finally, we're going to talk about how to balance data and how sometimes when you either over or undersample different categories of an outcome variable, you make it more likely that the model that you end up using really better understands the data. In this video, we're going to talk about how to modify model options. In this section, we're going to talk about how to improve individual models. In this first example, we're going to show how you could potentially improve a model by modifying the options within that model. Now here I already have my electronics data set and I have my partition node. Again, I'm using Modeler to demonstrate these techniques, but again, you could use whatever statistical or data mining software you have available. Now in this example, what I'm going to do is I'm going to use a support vector machine model. So I'm just going to go down to the modeling palette and I'm going to connect my partition node to the support vector machine model. Again, notice that I'm going to be predicting the variable status. Now if I edit my modeling node, I'm going to go over to the expert tab and I'm going to choose expert. As I've mentioned before, whenever you use a support vector machine model, you're always going to have to modify its settings because it really is a model where it's a bit of trial and error in terms of trying to get the settings correct. Now, what I'm going to do here is I'm going to change the regularization parameter from a 10 over to a 5. Like I said, that's generally where I like to start, and then I can see if I'm over or under fitting my model. And then previously, we talked about how there were 4 different types of transformations, 4 different kernel functions. And in our previous examples, we went through the most simple one, which is a linear transformation. And we also did the most complex, which was a sigmoid transformation. And what we found was that the linear transformation did a lot better job than the sigmoid transformation. And we hypothesized that it really was because our data was relatively simple. Well, let's go a step beyond just doing a linear transformation. Let's do a polynomial. Now with the polynomial transformation, it's a little more complex than a linear transformation, but not quite as complex as a sigmoid. So maybe this is a good fit. Now what I'm going to do here is I'm just going to run this on the defaults. Obviously I changed my regularization parameter to a 5, but everything else is a default for the polynomial function. I'm just going to click on run now and let's see what we get. The model has finally been completed. It took almost 9 minutes to build this model. Let's see how accurate this model is. I'm going to go down to the output palette and I'm going to connect my generated model over to an analysis node. And I'll edit the analysis node. And now I'm going to click on coincidence matrices for symbolic targets and then just click on run. You can see what we did here was that the accuracy for the training data set is extremely high. It's almost 97%. But notice how much it drops down for the testing data set. It drops down about 19%, which is huge. You know, like we talked about before, you generally want the results for the training and the testing data set to be similar, and you want them to really be within 5 percentage points of each other. Otherwise, your model is really capitalizing on chance, and it's really a model we're not going to be able to trust that much. But what is encouraging is that the results for the overall accuracy for the testing data set, they are 78%, which is higher than the 73% we had seen with the linear model. So maybe the polynomial model might do a better job than the linear model, but not the one that we currently have because we're really capitalizing on chance. So let's modify the settings of this model. To do that, I'm just going to close out of this window. I'm just going to edit my support vector machine model. And right now what we have, the degree set to 3. That means that we're looking for up to cubic functions, which may be a little too complex for this data. So let's just look for quadratic functions. So we'll change the degree value from a 3 over to a 2, and then we'll just click on run. This took about 4 minutes to build this second model. I'm going to run the analysis node. And you can see that the overall accuracy on the training data set is 84.6. In the testing data set, it's 80.2. So the numbers are, one, they're much more similar. They're within 5 percentage points of each other, so that's great. 2, the overall accuracy is actually up to 80%, compared to what we had with linear model, which was only at 73%, and the sigmoid function, its level of accuracy was in the 50s. And then we can see how well we're predicting each one of the different categories. So here at this point, we've been able to build an improved model by just modifying the options within that model. And we made a model that is, one, more consistent, and two, has a higher overall level of accuracy compared to previous versions of the model that we had built.